Hi students, welcome to Year 10 Science and the Space topic. This is video number 9, and this time I want to just quickly, review the historical developments in our models of the universe. Hopefully the most important thing that you will pick up here is the keys to why our models change and how often our understanding of the universe, the solar system and our place within it has continued to be refined over time. As we go through this very quick tour of the key contributors to our understanding of the universe, and certainly this is by no means an exhaustive list, trying to keep in mind the fact that sometimes models change because of additional evidence, because we have new data that we didn't have before. Sometimes we have better data. And sometimes related to the better data is we have better equipment or better technology. And the improvements in technology, particularly in the area of telescopes, not just optical, but also radio and telescopes detecting many different components of the electromagnetic spectrum. Also things like spectroscopes, which have given us information about the different emission spectra that we see from different stars, and that's helped us to make conclusions around things like redshift, Big Bang, and expanding universe. So all of these things are interconnected. But of course the other thing that can happen is you can have reinterpretations, which is the same data looked at with new eyes. Another scientist that comes along looks at the same set of data and actually sees a way of interpreting it in a different way. These two different areas, are keys to why sometimes our models do change and sometimes why our models need to change. So let's have a quick Cook's tour then through some of the key ideas. The whole idea of what's beyond the Earth has been around ever since people first looked up at the sky and wondered what was up there. Historically, we had a very geocentric idea about the universe. That is, we were the center, we are center, the Earth is at the center, and everything revolves around us, which is of course what it looks like from the Earth. Everything else looks like it's moving around us. We feel like we're stationary. We don't feel like we're moving at all, even though we are, and everything else revolves around us. This also fitted in with the ancient Greek idea of an unchanging universe, a specific number of spheres that carried the heavenly bodies, and circular motions as being the perfect ones. They were the natural ones. Even in this sphere, we had some, challenges to the ideas. So whilst Aristotle's very well known, Aristarchus not so well known, and yet partly he was a little bit ahead of his time. By studying changes, the fact that the moon changes its appearance in a regular, predictable kind of a way, it helped Aristarchus develop the first recorded ideas about the Earth not being the center of the universe. That is, the sun potentially as the center of the universe. The sun is bigger than the Earth, the other planets as well as the Earth orbit it, and the Earth actually rotates, which is what produces the apparent motion. The fact that it is rotating itself is what causes us to change our perspective, to look at different parts of the sky rather than the whole sky is moving around us. Aristarchus was also the first to predict parallax. We have looked at the fact that parallax is one of those things that happens when two objects, or an object appears to move in relation to its background, and we've done that just by lining your a finger up with the place on the opposite side of your room, close one eye and line it up, and then close that other eye and open the first one, and it looks like your finger has moved relative to the background. That's partly the parallax effect. The problem with Aristarchus is that he wasn't probably quite as well thought of as Aristotle, and so his ideas just sat around for a long time. Ptolemy started to put models together. So this was the epicycle model, and this was that the Earth at the center and then perfect circles. That isn't one I know, but also circles within circles. So sun, planets, moons, all circles within circles, all orbiting the Earth. The Earth was slightly off center, and this is what can affect the rates of planetary motion. So these were observations that were made and models that were designed to explain these observations. One of the things that was really interesting was the whole idea of retrograde motion. And instead of objects looking like they were moving through the sky, occasionally they looked like they were actually going backwards and then moving again. This retrograde or backwards motion has actually been noticed from the Earth of different types of heavenly bodies at different times and needed an explanation. The best explanation, whilst the epicycle one did have a little bit of a sway in how to explain retrograde motion, it was explained much more conveniently and convincingly by Copernicus, who moved the sun to the center of the solar system and the planets, including Earth, orbiting around it. It agreed with the observations that showed there was no stellar parallax, that parallax couldn't be achieved at that time, counter to some of the stuff that we talked about with Aristarchus. Leading on then was a man who, I guess, facilitated the most significant data collection that's happened certainly up to that time, and you could argue in terms of significance even since then. Tycho Brahe was so rich he bought himself an island, set up an observatory, and managed to gather a huge amount of detail. He tried to combine the Earth-centered, Sun-centered into a single kind of model. He didn't want to completely lose that idea of the Earth at the center with the planets revolving around the Sun. He said stars were unchanging and he too couldn't detect any parallax. A student of Tycho Brahe's was Johann Kepler, and Kepler was probably better at actually putting a lot of that data together, particularly in a way that made mathematical sense. One of the key contributions of Kepler was the fact that he looked at planets as moving in ellipses, not circles. So rather than orbiting in a nice perfect circle, the orbit was more of an ellipse. And that explained a lot of the motions much, much better than circular motion. Of course, this also tells us something about planets and their relative motion in terms of the ones that are closest move quickest, and the ones that are further away take more time, move more slowly, take a long time to orbit the Sun. So it helped us to develop a couple of laws of planetary motion, and these are very, very important in terms of what we then looked at in terms of our understanding of the solar system. This contributor, Galileo, gave us one of the most important tools that helped to shape our models after this. So now we have technology affecting our models. The technology allowed Galileo to look at a huge number of things that were not seen before, because we just didn't have the ability to do that. So he described the largest moons of Jupiter. He saw or identified the rings of Saturn. He picked up sunspots. He noticed that the moon has craters and mountains, and that Venus, like the moon, goes through different phases. This technology changed our understanding because of the fact that we now are able to see things in a way we'd never seen them before. That led on to Isaac Newton, and Newton, we've spent a lot of time talking about his laws of motion, his 3 laws, which I hope you will have all sitting on the top of your head now, and the fact that we can apply those laws not only to objects that move on the Earth, but also to objects out in space. Because of the speed of most of those objects, Newton's laws not only were relevant then, but are still relevant now after the work of Albert Einstein. And of course, he's the most critical last one. Einstein's theory of relativity, both general and special, told us something about the frame of reference, where we are when we look at objects in motion, whether we are in the same frame that we're moving as they are moving, or whether that we're in a different frame and we're watching them move relative to us. He also talked about the interchange between energy and matter, E equals mc squared, which really made us change our whole understanding of motion. It also significantly changed the way we looked at the universe and the objects within it. We looked in one of the previous videos at the consequence of that in relation to the bending of light by large gravitationally strong objects. After Einstein, and I guess in following on from a lot of his work, we continued to develop more and better telescopes that we could look deeper into space. We started to put some of these into space, so we now were able to get past the Earth's atmosphere, which has quite a debilitating effect on the light, which can sometimes be very faint coming from stars that are very distant, and therefore can be dispersed and we can't pick it up as readily on the Earth. But we've got better technology to do that. We've also got technology out in space that's less affected by some of those problems. So hopefully this has been a long video. You may fast forward, or you may have already got to the end by now. And hopefully it gives you a quick idea. The most important things to remember, of course, is how models change on the basis of the information that we gather or the interpretations that we place on that data. Thanks for watching.